In this video, we are going to be learning about cis and trans isomers. This will help us with our learning objective for learning how to draw the expanded structural formula, condensed structural formula, and line angle structural formulas for all of our different hydrocarbons, as well as identifying the molecular geometry around carbons. Single bonds are free to rotate. So if you have a zigzaggy line here, this is free to rotate, and you can instead flip it up. Like, that's totally cool. Single bonds can rotate. It's like putting one fingertip on each hand together. You can rotate your fingers around without ripping your fingers apart. But if you put two fingers together like a double bond and try to rotate your hands, then your fingers get all twisted. Double bonds and triple bonds cannot rotate. They are fixed in their locations. Since they cannot rotate, then there's some different isomerization possible for alkenes. Alkenes have two groups on each end for each carbon, and then we call a side when it's like across the double bond. These are rigid. It cannot rotate, so we cannot flip the location of E and D. Those are fixed in here. Alkynes are linear, and so they do not have this cis and trans isomerization possible because there's only one group on each carbon. For cis and trans isomers, we need these groups on there. Cis isomers means that those groups are on the same side of the double bond. And so we said same side. So this is like the same side of a double bond, not the same end, the same side. Like it has to be like on each carbon. These are across from the double bond. If you're ever in doubt of what to look for, you can always focus on the location of the hydrogens on here. You see those are on the same side, and now these are on opposite sides of the double bond. And so trans always means like across, opposite, transportation, like transcontinental. It always means like across. And cis means the same side. And so cis is the same, trans is opposite sides. Those are two different compounds. Cis and trans isomers are not possible for all alkenes. Alkenes, it depends on how many groups there are on here. We need unique substances. If we imagine this molecule having a little bar down its center, and we rotate it around, and we flip it so that this CH2CH3 is up here, then this is identical because those two hydrogens, like if this was that hydrogen and then we rotate it around, now that hydrogen's up here. But it's the same molecule. So it's not like we can draw the trans isomer just by moving this up. That's not going to get us a trans isomer. That's just going to get us the same molecule back again, because that is just a rotation of the previous molecule. Instead, we need to have different groups on these carbons. So if on each end, if A and B are different from each other, and C and D are different from each other, then we can have cis and trans isomerization possible. So you need different groups on each carbon. A and C could be the same, A and D could be the same, that's okay. But A and B need to be different, and C and D must be different. So which of these would be the cis isomer of dibromo-2-butene? Go ahead and pause the video and try to decide which one is the cis isomer. All right, the cis isomer is option C because these need to be on the same side of the molecule. This is not the cis isomer of that. It's not a cis isomer at all. These are on the same carbon, and we need them to be on different carbons. This is the trans isomer because they are on different carbons, but they are across from one another. So this brings us to a different category of isomerization than we have seen before. Before we talked about constitutional isomers. Constitutional isomers have a different bonding connectivity. So they differ in the way that the atoms are bonded to one another. So for instance, 1-butene is an isomer of cis-2-butene because this molecule has a double bond between carbons 1, this double bond is between carbons 2 and 3, whereas this double bond is beginning at carbon number 1. They have the same molecular formula, so that they are isomers, but the location of the double bond is different. That makes them constitutional isomers. Cis and trans isomers still have the same connectivity, meaning the substituents are off the same number carbon, and the location of the double bond is the same in both molecules. So it's still a 2-butene. What's different is saying the locations of these, whether they are cis or trans from one another. And that brings us to stereoisomers. Stereoisomers are isomers that only differ in the 3D arrangement of their atoms. The connectivity is the same. I'll just write that down. Same connectivity. So we saw the nutrition label earlier that showed how much saturated fat was in food and how much unsaturated fat was in food. And it also showed on the nutrition label trans fat. Now, anything that's not trans fat or saturated fat must be cis fat, and cis fat's not on the nutrition label. So here's the structure of olive oil. And I want you to pause the video and answer these 3 questions. What functional group makes it an acid? What makes it unsaturated? And is it cis or trans? Okay, so the functional group that makes it an acid is this carboxylic acid. That's the fatty acid that makes it an acid. Here's the location of the double bond, and so the double bond makes it unsaturated. And we can see here that those 2 lines are coming out in the same direction, and so that makes it cis. A trans fat would look like this, where this and that are coming out on opposite directions. Sometimes it helps to turn your head so that the double bond is flat. So if you turned that image, it would look like that. You gotta rotate your head so that you can see that those are coming out on opposite directions, and these are coming out in the same direction.